Today we're going to talk about the Earth, not from a geographical standpoint, but treating it rather as a small, isolated object in space, which, of course, is just what it is. As such an object, the Earth has a number of motions and gyrations, which are important to the Earth, of course, and to all of us because we live on the Earth. Here are a couple of models which are going to tell us something about these motions. This one is precession. This one illustrates the Earth line, and we'll talk some more about both of those things later on. The Earth is one of a group of small objects in space that are moving about the sun under its control. It is the third of the planets in distance from the sun. There are 9 planets in this system called the solar system. Here they are. Here is the sun. Here are the smaller planets, Mercury, Venus, and the Earth, number 3. Then comes Mars. Then outside of Mars is a belt in which travel a great many minor planets, the asteroids. Then, beginning at about 500 million miles from the sun, we come to the realm of the giant planets, Jupiter, Saturn, Uranus, and Neptune. And finally, last of all, there is another small planet, Pluto. Interspersed among these things are a great many other small objects, the meteors and comets. Now, there is a wide diversity of sizes in the objects in the solar system. The sun, the star that controls the motions of all the other bodies, is, of course, the largest. Here is a segment of the sun on the same size scale as the others. The sun has much more than 99% of all the material in the solar system. Here are the small planets, Mercury, Venus, the Earth, Mars, and, at the other end of the distance scale, Pluto. Then here are the giants, Jupiter, Saturn, Uranus, and Neptune. The Earth goes about the sun on a path or orbit which is not a circle but an ellipse, as is the case with the paths or orbits of all the planets. That means that at one time in its journey about the sun, the Earth is a great deal nearer the sun than at the other time. When the Earth is at the nearest point to the sun in its orbit, the point that astronomers call perihelion, it is 91.5 million miles from the sun. At the other end of the scale, when the Earth reaches the most distant point in its orbit from the sun, it is 94.5 million miles from the sun. The mean distance, that is the middle between these two extremes, is 93 million miles, and that's the distance we usually use in speaking about the Earth's distance from the sun. The Earth travels about the sun in a period of time that we call a year, which is 365 days, 5 hours, 48 minutes, and 46 seconds. And in order to make that trip on time and be ready to start all over again at midnight on December 31st every year, the Earth has to go 18.5 miles a second. Now, a little simple arithmetic will tell you that if the Earth travels 18.5 miles every second of a year, the year has a few more than 31 million seconds, the Earth takes a trip of 600 million miles a year, and you all go along. So don't let anybody call you a stay-at-home. You travel. Now, the Earth's orbit about the sun, while it is elliptical, is not an ellipse on one plane. In this model, you can see these lines. They are the apparent paths of the Earth about the sun. Actually, this part of the Earth's speed of 18.5 miles a second is contributed to by the sun's own speed of 12 miles a second traveling through space. And the sun's path is the straight line in the middle. Really, the Earth travels going along with the sun in a very much elongated spiral ellipse. You can see it here. This is the route that the Earth takes through 1 year, traveling with the sun. This is called the Earth line. The Earth weighs 6,600 million tons. That makes it pretty heavy. In fact, it weighs about 5¼ times as much as the same amount of water would weigh. If we were to take a piece of all the planets, the same size, and weigh it, that piece that we got from the Earth would be the heaviest of them all. Now, the part of the Earth that we're familiar with, that we can see, that we walk around on, is considerably less dense, less concentrated than the Earth as a whole. That makes us quite sure that the Earth must have a pretty heavy, pretty solid center. We have proved that to some extent by sending shock waves down through the Earth and recording the effects of these waves on seismograph machines. Now here's the Earth. Let's take the top off and see what it looks like underneath. There it is, a core probably of iron or nickel iron. And at the temperatures that we know exist in there, about 5,000 degrees Fahrenheit, this must be molten. But at the same time, there's a tremendous pressure on it. The pressure, even as little as 25 miles in from the top of the Earth, is about 10,000 pounds per square foot. So while this is fluid and molten, it is still pretty heavily compressed. Around that center core, there is a rather thick layer of stony material. And above that, another layer, not so thick, of granite and volcanic rock. And of course, the surface of the Earth has been affected by the atmosphere around it, so that it is what we might call dirt. Now, this concentration of material in one small volume, this mass of the Earth, is responsible to some extent for the surface gravity of the Earth, that strange pulling power that keeps us on the surface of the Earth and, of course, everything else. It also makes it necessary for any projectile, any vehicle that is intended to escape entirely from the Earth out into space, to reach a velocity of about 7 miles a second. And that, of course, contributes to the difficulties of launching satellites. This same surface gravity of the Earth, combined with certain effects of the Earth's atmosphere, give us water on the surface of the Earth. And the Earth is the only planet in the solar system that we are sure has water upon it. We know that Mercury, nearest the Sun, is perfectly dry. We are not sure about Venus. We've never seen the surface of Venus. All we can see is a cloak of dense, white, impenetrable clouds. But we have never been able to isolate, to locate any water vapor or oxygen in that atmosphere of Venus. Mars has moisture, but not water. The giant planets, while they are supposed to have a very thick sheath of ice around their cores, are so far from the sun that the temperature never gets down up high enough for that ice to melt. This same surface gravity that keeps water on the Earth also holds upon the Earth an envelope of gases that is our atmosphere. Now, the atmosphere is made up of about 78% of nitrogen, 21% of oxygen, and the remaining is composed of traces of several other elements, fortunately beneficial to us. Here are some of the things that happen in that layer of atmosphere which is closest to the Earth. This is called the troposphere. That means the sphere of change or turning, and it is where all our weather occurs. Now, this atmosphere of ours is often used as an example of lightness, lack of weight. Trifles light as air, Shakespeare said. But that isn't so. The atmosphere weighs upon every one of us with a weight of about 15 pounds for every square inch of surface. And most of us have enough square inches of surface in our makeups so that we are constantly supporting a weight of about 14 tons. Now, let's talk about that atmosphere of ours. Here is a picture of it. Here is the Earth, and here is the atmosphere. We believe that the atmosphere extends up to about 800 or 900 miles above the surface of the Earth. We believe that because we can see the aurora, the northern or southern lights at that height. And we know that the aurora is a phenomenon of the atmosphere. Of course, the atmosphere becomes increasingly dense, increasingly less dense as we leave the Earth and go up. Actually, the air is denser at our feet than it is at our head. And of course, that change in density makes projects like the climbing of Mount Everest, for example, very difficult. And it means that airplanes flying above 10,000 feet, which is not quite 2 miles, should have oxygen equipment. The lowest level of this atmosphere is that troposphere that we met a little while ago, the sphere of turning. And almost all of the motion of the atmosphere lies in this layer. As I said before, this is where our weather is. The temperature at the troposphere drops gradually up to a height of 8 or 10 miles, which is as far as that layer goes, until it gets about 50 below zero. Above that is the stratosphere, the sphere of levels, of layers. There, the temperature rises slowly until it gets about 70 above zero at the top of the stratosphere. And it is up in this level, near this level, that these jet streams travel, these strange winds that whip along at 200 miles an hour and that we didn't know anything about a few years ago. Above the stratosphere is a layer, unbelievably tenuous, thin, called the ionosphere. Now, that's a name that's going to need a little bit of explaining. What is an ionosphere, and what does the name mean? Well, here is an atom, slightly enlarged, of course. This is an oxygen atom. All atoms are essentially similar in that they have a closely knit group of particles, protons and neutrons and others, which form the nucleus of the atom. Around that nucleus travel other particles, the electrons, which have no mass at all. All of the mass of the atom is here. When an atom is working properly, it looks something like this, with a haze of electrons traveling around the nucleus. Now, in the ionosphere, the atoms there are subjected to a continual, rather brutal bombardment of particles from the sun, which sometimes knock off one or more electrons from each atom. Now, an electron separated from the atom is an ion, and the rest of the atom without its electron is an ion. And this bombardment of those upper levels has caused the separation of many electrons from their atoms, and they and the remaining part of the atom are the ions. Layers in this sphere, in this level, the ionosphere, are responsible for example, the excellence of the reception of our radio programs. When the ionosphere is disrupted by this bombardment of the sun, its reflecting power is destroyed, and we don't get the radio programs, for example, that are reflected up from the broadcasting station down again to our receivers. We think that this same bombardment is also responsible for the aurora. Above the ionosphere, of course, is the exosphere, the border of outer space. In the troposphere, again, is our blue sky. Now, that blue sky is simply the result of impurities in the atmosphere, tiny particles of matter, little bubbles of water, which give us, by their action on the rays of the sun, a sort of a deceptive dazzle that we call the blue sky, and which hides the real sky from us. The real sky is black, with the blackness of space. And if you get up high enough, and you don't have to go very high, 10 or 12 miles, you can see that sky. Now, here are 4 frames from a motion picture film. Look at them closely. You can see the blue sky. See that level of light and where it ends? That is our blue sky. Blue because it is dirty. The Earth's rotation in space, the spinning of the Earth upon its axis, gives us that alternation of light and dark that we call day and night. Now, as the Earth spins, of course, it carries us, wherever we are on the Earth, alternately into and out of light and dark. And we have taken that period of time that it takes the Earth to make one complete spin upon its axis, and we call it a day, and we've divided it up into 24 of our hours. Now, while the Earth is making that one spin, the definite length of time it takes that, the Earth is also, as you see, moving around the sun a little bit in its journey around the sun. Now, that means that the Earth is also traveling on all during a day, and that has an effect upon the way we see the stars at night. For example, suppose we start the Earth here, and here is a star. Now, the Earth is spinning this way, in the way that we call stars fall on other places beside Alabama, what we call west to east. The Earth is also moving around its orbit around the sun in the same direction, from west to east. Now, suppose we are standing here, just, you see, as we are passing from sunlight into starlight, and we see the star. And as the Earth turns through the night, it also moves around, and the next night we see the star again, but we get to that point earlier than we did the night before, about 4 minutes earlier. Now, that is the way we figure time by the stars. Time by the sun we have called 24 hours. Then we found that time by the stars was a little bit shorter because we overtook the star each day. That is sidereal time, from the Latin word sidus, one of the Latin words for star. And instead of being 24 hours, it's 23 hours and 56 minutes and a few seconds. That is sidereal time. Now, as it goes around the sun, notice that the Earth is not standing up straight. It's tipped away from the vertical. That is what we call the inclination of the Earth's axis. And that inclination, that tip, does not change materially during the year. Remember that word materially. That's an important one. Here we see the Earth during a winter year, and this is why. You see, the North Pole of the Earth points to a certain place in the sky. There is a fairly bright star standing in the sky right over the extension of the Earth's North Pole. That's the North Star, a star in the constellation of Ursa Minor, the Little Bear. Now, all of you know, I'm sure, that you can see the North Star over the extension of the Earth's pole every night in the year. It doesn't move around materially. This is what happens, though. The Earth does move around the sun, and because the axis of the Earth is always tipped in the same direction regarding the stars, it changes regarding the sun. Now watch. Here we are in December. The northern end of the Earth, because of that tilt, is then tipped slightly away from the sun. Up where we live, in the United States, in Europe, in Asia, it's winter. Because, you see, the sun's rays are striking that part of the Earth at a slant. Down here, in the southern half of the Earth, South Africa, Australia, South America, it's summer, because they are getting the rays directly at a point south of the equator. The year begins. We go on around. Now notice that the tilt of that axis will always be parallel to its position anywhere around. It doesn't change. And as we get around 3 months after we started here, we come to a place where the axis, still pointing at the North Star, this time is tipped neither toward nor away from the sun. That is the beginning of spring. The sun then is seen from the Earth overhead at the equator, and it's the 21st of March. So the year keeps on going. It doesn't pause there for us to look things over, but it keeps right on going. We have to catch that instant in passing, as it were. And we get around another quarter of a year. Now notice what's happening. The axis is still tipped in the same way it was. That hasn't changed materially. So at this time, we have the upper end of the Earth, the northern end, where we live, tipped toward the sun. It's summer up here, we're getting the direct rays. It's winter in the southern hemisphere, they're getting the slanting rays. And we keep on going around and we come to a point opposite to where we were in March, where again, that unchanging tilt, not changing materially, is neither toward nor away from the sun, and we have the beginning of autumn, the 22nd of September, and so on. The end of the cycle, of course, occurs when the Earth has completed one revolution about the sun. We get back to that point where the northern half is tilted away from the sun, and it's winter again where we are. Here is the diagram of that same effect. Here's the Earth in June. Here's the tilt of the axis. You see, it's not vertical. Here's the equator, here's the pole, and we live a little less than halfway between the equator and the pole. And you see, in June, we're getting the direct rays. They're hitting the Earth at right angles. Down here, below the equator, South America and so on, they're getting the rays at a long slant, and they don't do nearly as efficient a job of warming up the surface of the Earth. In December, you see the reverse is true. Notice the axis pointing precisely the same way that it was in June, but this time away from the sun. And here, down in South America, they're having summer. They're getting the rays at right angles to the surface of the Earth. We're getting them on a long slant, and it's much cooler. Now, as the Earth goes around the sun, of course, as we said, there are times when it is closer to the sun than the other. The time when the Earth is nearest the sun occurs in our wintertime, usually early in January, about the 4th or 5th of January. You'd think that would make a difference. We're nearer the sun in winter, but it's colder. Well, the tip of the Earth, the seasonal tip, counterbalances that. But by the same token, it's summer down in the southern hemisphere. See? When it's winter in the southern hemisphere, the Earth is far from the sun. And again, that seasonal tip compensates us who live in the northern hemisphere for that. But it makes the southern winters colder. The coldest temperature we have ever found on the Earth is at the South Pole, where it's 120 degrees below zero. The northern temperatures are about 30 degrees warmer. Now, long ago, when the Earth was very young and a little softer than it is now, it was also rotating much more rapidly, making a complete turn in about 5 hours instead of 24. That whizzing around forced some of the soft material of the Earth into a belt around the Earth's equator. Here's what happens. Here is an outline of a sphere made of flexible metal strips, and it's very easy to bend, you see. But you can do that same thing by spinning it. Watch. See that? That makes the Earth oblate. This same distortion affects many of the larger planets because they are rotating very rapidly and fluid. That means that the Earth has acquired a belt of excess material around its equator, around its waist, which could happen to the best of us. Now, the sun and the moon, and principally the moon, are not lined up in space with the equator of the Earth. They are on a different plane. We've got a model over here. Remember that precession model, which will show you that. Here it is. And you see they've built a belt of excess material around this Earth. Now, this is the plane, the level at which the moon and the sun generally operate. Suppose we spin this Earth, tilting it just as it's tilted in reality. I'll just spin it, get it going well, and then let go of it. Now watch what happens. Do you see that motion of the pole of the Earth? That is the Earth's effort to counterbalance by spinning the gravitational pull of the sun and the moon upon the excess material around the equator of the Earth. This causes the poles to sweep out great slow circles against the sky. Circles which take 28,500 years to complete, to go once around. That means that since the pole actually does very slowly point to a different part of the sky, we should see a different North Star from time to time. We do. We're working on the third of our North Stars now, within man's history, that is. This is called precession, and it affects our view of the stars constantly through the sky. Now, there is one arbitrary point in the sky, that point at which the sun seems to stand against the stars when it crosses the equator from south to north on the first day of spring. That is called the precession of the equinoxes, then, because it makes that equinox seem to slip westward through the skies very, very slowly. Here's what happens. Here's a diagram of it. Here you see the Earth with that same old familiar tip away from the vertical of its axis. Here is the equator with its excess material. Here is the moon, not on the plane of the equator, pulling the equator down when it's on this side, up when it's on that side, but in the same direction, trying to straighten that out, to bring the equator on the same level. The Earth's resistance to that pull gives it that slow oscillation, that wobble, which gives us the precession of the equinoxes. We have no idea what the Earth looks like in space, when it's really out in space. We do have some photographs taken from rockets, which definitely show the curvature of the Earth and show its tremendous cloud cover. And there are some films which have been taken from rockets which show that same thing and also show the blue sky. See them? Now, we know that half of the Earth, but not the same half, fortunately, is constantly covered with clouds. That would make the Earth a white, hazy object with a tinge of blue, that same blue which is the blue sky, because blue sky works both ways. When you're underneath it, you look up and you see it. When you're outside of it, you look down and you see that blue haze around the Earth. Now, let's sum up a little bit and see what we have talked about today. First of all, we have found out that life can exist only under a rather narrow range of circumstances. It must have a certain range of temperature. It cannot exist below 40 degrees below zero or above 120 degrees above zero. Life must have oxygen and other nutritious gases to use. Life must have water, and life must have energy in the form of radiation. The Earth is the only one of the 9 planets which is situated at just the precise distance from its mother star, the Sun, which has just the correct mass to hold these nourishing elements upon its surface to make life possible there. The source of the Earth's temperature is the Sun, and if we were too close, it would be too little. If we were too far away, it would be too cold. The source of the Earth's atmosphere is the Earth's own mass, its power to attract these gases to its surface. And that, in a great measure, is the secret of the water on the Earth. The energy, that radiation, which contributes so much to life on the Earth, comes to us from the Sun. This is the Earth, the abode of life. We do not know, certainly, whether there are any other planets anywhere that have life upon them. But we know that there are so many stars which are very much like the Sun that it seems impossible that some, perhaps many of these stars should not have a family of planets very much like the Sun has. And in these families there must be many planets which are at just those critical distances, which have just that mass, which have just the right circumstances to give them life. There must be somewhere out among other stars, perhaps one that we can see at night, other planets with life like the Earth.
This is National Educational Television.